All right, let's dive into a question that comes up all the time in machine learning. You're trying to find something weird in your data, an anomaly. So, do you reach for an anomaly detection algorithm or do you stick with a classic supervised learning approach? Let's figure that out.
So let's just get right to the heart of it. Because it's a super logical question, right? You've got data, some of it is labeled normal, your negative examples, and some of it is labeled anomaly, your positive examples. I mean, that just screams classification problem, doesn't it? So why on earth wouldn't you just use a standard supervised learning algorithm to sort them out? Well, as you'll see, it's not quite that simple.
You can think of this as a tale of two very different but very powerful algorithms. They're both great tools, but they operate on completely different principles. And picking the right one, it's absolutely crucial. It all boils down to your data and what exactly you're trying to find. So here's what we're going to do. We're going to walk through just two critical questions. That's it, just two. And by the time we're done, you'll have this simple mental framework that'll let you look at any problem like this and know exactly which tool to reach for. Okay, question number one. It's all about the numbers. It's about the balance, or more likely, the imbalance, between the normal stuff and the weird stuff in your dataset. Think about a standard supervised learning algorithm, something like logistic regression. It's hungry for data. It needs a good, healthy chunk of both positive examples, the anomalies you're hunting for, and negative examples, the normal stuff. That's how it learns to draw a clear line between the two. And now look at the complete opposite picture. This is where anomaly detection lives. It's built for a totally different world, a world where you have tons and tons of normal negative data, but only a tiny, tiny handful of positive examples. We're talking maybe 50, 20, heck, maybe even none at all. It's a massive imbalance. So here's the brilliant trick. Instead of trying to learn what an anomaly looks like from just a few examples, which would be almost impossible, anomaly detection completely flips the problem on its head. It takes all that normal data you have and builds a super precise model of what normal is supposed to look like. Then its job is simple. Anything that shows up and doesn't fit that model, bam, it gets flagged as an anomaly. So you might be asking, what about those few anomaly examples I do have? Well, this is key. You don't touch them during training. They're too precious for that. You hold them back. You save them for your evaluation, for your cross-validation and test sets, to see if your model is actually any good at spotting the weird stuff. They're your report card, not your study guide. All right, that was question one, data imbalance. Now for our second, equally critical question. This one is all about the future. We have to ask ourselves, what will our future anomalies actually look like? Are they predictable? And this quote really says it all, doesn't it? Future anomalies may look nothing like the ones you've seen so far. Sometimes the failure you're going to have tomorrow is a kind of failure that the world has literally never seen before. And this is where the two methods really, truly part ways. So supervised learning is fantastic for what we could call the known unknowns. A perfect example is spam email. You've got your phishing scams, your sketchy sales pitches, malicious links. There are lots of types. But if you have a giant data set, your algorithm has probably seen thousands of examples of each. So the spam you get tomorrow is probably going to look a lot like the spam you've seen before. Anomaly detection, though, that's for the unknown unknowns, the real curveballs. These are the problems you couldn't even predict if you tried. The algorithm isn't trying to match a pattern it already knows. It's looking for any significant deviation from normal, even one that's brand spanking new. And this analogy just nails the difference. Think about an aircraft engine. There are a million ways it can fail, right? A tiny crack here, an overheating component there, and a completely new type of failure could pop up tomorrow that has never happened in the history of aviation. That is a job for anomaly detection. Now think about spam. Yeah, it's diverse, but with enough data, you've pretty much seen all the tricks. That's a job for supervised learning. Okay, so we've looked at our two big questions, the data imbalance and the nature of future anomalies. Now let's just snap it all together into a super simple framework you can use to make the right call every time. And here it is, all laid out. This chart basically says it all. You look at your positive examples. Are they super rare, like 0 to 50? And could your future anomalies be totally new? If yes and yes, you go with anomaly detection. But if you have a solid number of both positive and negative examples, and future problems will probably look like old problems, then you go with supervised learning. It really is that clear. So let's make this real. Where do you use anomaly detection?
Think fraud detection, especially when you're starting out and have few examples. Or manufacturing quality control, looking for that 1 in a million defective part. Or monitoring a giant data center for a machine that's about to fail in a way you've never seen before. And supervised learning. That's your go-to for things we already talked about, like spam filtering, or weather prediction, or classifying cancer tumors, where, thankfully, we have large historical data sets.
But, and this is a really important point, the right tool for the job can actually change over time. Imagine you're a small startup. You'd probably use anomaly detection to spot fraud because you just don't have many examples. But fast forward a few years and you're a massive e-commerce site. Suddenly, you've collected thousands of examples of different kinds of fraud. Well, guess what? Your problem might have just graduated into a supervised learning problem. So let's boil this all down to a simple 3-step mental checklist you can take with you. Step 1, count your positive examples. Is that number tiny? Step 2, think about your future anomalies. Could they be something completely out of left field? And step 3, based on those 2 answers, you choose your tool. That's it. That's the whole decision process right there. Which kind of leaves us with one last big question to think about. As our world gets more and more complex, with intricate supply chains, new AI systems, all of it, is our ability to spot the problems we've never seen before, to find those true unknown unknowns, becoming maybe the single most important skill we need to build for the future?